do you want to lick my balls?
No.
Fire's half a year old. It's kind of hot.
No.
Nice ass, Toadette.
Yeah.
Smash my balls sexually. I want to fuck your massive fancy dick. Finn likes minors. Real. Oh, fuck. I didn't think that was actually going to come for me.
That's shit.
I like
That is
your
shit.
fancy dick. I'm going to whip your ass.
Finn, how often do you jerk off?
Fucking twice a week, I guess. I think he'll come through. Minors are my favourite. I love going to the park just to fuck some young girls. Please, I'll fuck you up. I'll fuck you up. I'll fuck you up. Like that.
Sorry, I'm looking at something way more important.
No, I like baby. I love baby. I feel I'm 1 year old. That's kind of hot.
Oh,
Suck
no.
my fucking cock.
That is a dislike.
Hey, Fire, nice ass. Finn, do you love young girls? Obviously. Oh, he's got a star as well. Fucking kill yourself. Fuck you, Fire, you dickhead. Even
Wow. I'm here. I forgot to log out indeed. Right. Let's do this shit then, baby. Yeah, okay. Lads, is it ads for you right now? Is it ads for you right now or nah? This ain't gonna be good. Please react again. I had ads. I'm not reacting to that shit again, Nastig. Anyway, you can rewatch the VOD if you want. Right. Let's do this shit, boys. Let's do this shit. Yeah, I need to time it, so I need to lock in. Clock. It's about negative metal ions. You'll find out, mate. And I want you to ask questions at the end, not in the middle, obviously. But I need to get this shit under 13 minutes. It's way too long right now. So, yeah, here we go. Right. Hello. Hello and welcome to my presentation on exploring the conformations of cone snail venom using molecular dynamics. So what is cone snail venom? Well, they're called conotoxins and they're produced by marine cone snails. They're competitive inhibitors of this, the human nicotinoacetylcholine receptor, and there's currently no available antitoxin. So 26% of stings are fatal. You can see this is alpha G1. It's one of the conotoxins, the most populated cone snail. It's the cone snail with the highest concentration when it injects you with its harpoon. Yes, it has a harpoon, I know. Right. It binds here in these pores between this alpha and gamma substates and this delta and alpha substates. These are highly constrained cyclic peptides, and you can see that here between these cysteines. They have disulfide bonds between this cysteine 2 and 7 and 3 and 13. Now, this is highly constrained, and because of this, it's believed that it just binds as is. So this alpha G1 molecule will just bind straight to the nicotinoacetylcholine receptor and cause permanent lung damage and even lung failure. So essentially, if you get stung by one of these cone snails, you go on a respirator for about a month, maybe more, and you just hope you survive. So obviously, the conformations are key to understanding the binding that occurs in these sites. And if we understand the binding, then we can invent a more competitive inhibitor that outcompetes all the conotoxins, and that would be an antitoxin. So that's what we're doing. And how are we going to do it? How are we going to explore these conformations? Well, we're going to use molecular dynamics, and it involves iteratively solving Newton's laws of motion in silico. And conventional molecular dynamics is extremely computationally expensive and takes forever. Realistically, you cannot find the entire conformational space of a biomolecule because of these so-called rare events. Systems commonly get trapped in these energy minima that are about 8 to 12 kilocalories per mole in these tier 0 dynamics. And essentially what that means is that these biomolecules take microseconds to milliseconds or even longer to go over these large energy barriers. And so we used a technique called enhanced sampling, which kind of does what it says on the tin, but it's used to speed up these rare events. And as you can see here, this is a CMD simulation. You're not seeing much movement, but this is an enhanced sampling simulation where the configuration is all over the place. But that's good because we want to explore more of the conformational space in less time, and that's important. So I use two different molecular dynamics enhanced sampling techniques, and we're going to learn about those now. One of them, the first one, GAMD, or Gaussian Accelerated Molecular Dynamics, is an enhanced sampling technique that smoothens this potential energy surface. So as you can see here, this is the original PMF in red. This is a very simplified system, a simple system even. And as you apply more of this, what's called a boost potential, you raise these minima out of these large energy barriers, and so these molecules can more easily explore this conformational space because of the lower energy barriers, right? Statistically, they're more likely to go over these barriers. But this requires reweighting to obtain the original potential. So you have to go back, obviously, to that original PMF, otherwise you've got something completely wrong, essentially. And the other one is REST2, or replica exchange with solute scaling. Essentially, you heat up the solute over a range of temperatures, and you can exchange between these replicas. So here you see T1 will be the temperature that you want to measure at. So basically 310 Kelvin for physiological conditions. And then you have these higher temperature replicas, and because these higher temperatures have more kinetic energy, these can also more easily explore the conformational space. So essentially, you can find more minima more easily at these higher temperatures, and then when a convergence criterion is met, you can exchange between them. So this T3 and T4, you can see here that they swap, and now this what was at a higher temperature is now at a lower temperature, and this T3 replica can explore this conformational space more accurately because it's moving around less because it's got a lower temperature. Its kinetic energy is lower, so it's going to explore it more robustly. And this is why REST2 is a lot more frequently used, and it's a lot more robust because there's no need to reweight like there is in GAMD. But it's a lot more computationally expensive. That's the main issue with it. So here's a generic GAMD workflow. This is what I did. You prepare your files, which is a PDB file, a protein data bank file. You solvate that to get physiological conditions. Then you minimize, which is important, and then you equilibrate using this NVT and MBT. The canonical and isobaric isothermal ensemble. These are equilibration stages that essentially what you do is you buy the property. Sorry, that's a meme. They give you the property even. No. Fuck, I shouldn't have said that because now I've thrown myself off. Bollocks! Fucking hell! So essentially what you do is you buy the property. Fuck! Right, let's go back just a minute. Let's go back just a minute. Fuck! I can't believe I said that. I just throw myself off so bad. That's why I can't stream and do this shit. Fuck. Finn, your shit presentation. I am if I do that. I am cooked if I do that. I cannot. I only said it because I was streaming. Did I make this presentation just for Lastic? No, I have to do it tomorrow. Swim too. How to bore someone to death. Present a PowerPoint with a bunch of bulleted points. What the fuck? What are you on about? This hasn't even got any bullet. It's got one bullet point in this whole slide. Oh well. Right. I'm going to continue from where I was. I don't know where I was actually. Oh, I was on this equilibration stage. Right, let's continue. I don't care what you got to say. Right. After equilibration, you put it into the GAMD runner. And you do these CMD preps, so you calculate the potential statistics, so you get the standard deviation of the boost potential and the minimum and the maximum and the mean, and then that's used to calculate the boost potential. Then you apply it in this equilibration stage, which then you further update those potential statistics periodically to arrive at a final boost potential that you apply in your GAMD production, which is what you're using to actually measure your system. And you typically need to repeat this because these simulations take forever. I simulated a microsecond with about 4,000 atoms maybe, and it took a day, or not even 5 days to do. So you have to repeat it because HPC only allows you to simulate for 2.5 days. So obviously it takes 2 repeats. You've got to concatenate your data. You get your bias results, and then you can do principal component analysis, or PCA, which is a dimensionality reduction technique. And essentially what this does is it allows us to see the main movements of the system. It's very simple, very easy to do. It's all about covariance matrices. And then you reweight and you get your unbiased results. So, simple, isn't it? But the problem comes from the reweighting of GAMD. Essentially, when you take these flattened potential energy surfaces and you want to recover the true sampling, you have to undergo reweighting, right? So there's 2 different types of errors that come along with this. When you're creating these histograms, obviously your bin size is what you use to create these histograms, and the standard error is given by this SE of the standard deviation in bin J over the amount of the square root of the amount of sampling in that bin. So essentially, you want as much sampling as possible to lower this standard error as much as possible, right? You want the standard error to be low, and we want it to be under 0.02 kilocalories per mole to consider it accurate, right? And also this gamma here is to do with the anharmonicity, and when that's above 0.01, you have unincorporated higher order effects such as like kurtosis and skewness. And obviously, when we were doing Gaussian accelerated molecular dynamics, the Gaussian part means we're assuming it's harmonic. So if we can't take that, if the potential, if the boost potential is not harmonic, then we get massive errors. And you can see here in this 20 nanosecond simulation of alanine dipeptide, when we're simulating this phi and psi angles and we're trying to work out the PMF after reweighting, this alpha L state that's surrounded by these large energy barriers is getting sampled less. It's getting sampled less than we would like. And because of this, we have these this anharmonicity. The minimum anharmonicity of this alpha L state is 0.1. So that's really, really high. And that considers there's a lot of skewness and kurtosis going on, or unincorporated higher order effects in that minima. So we can consider this alpha L state to be very, very high in error, essentially. And that's the original Gaussian accelerated molecular dynamics paper. So that's, you know, this technique is kind of used poorly, scientifically poorly, to say the least. So I use variable density reweighting. Essentially, you take your smoothened potential energy surface. You can see here, all these states are kind of similar in energy, and you can imagine how a molecule could easily change conformations over this state, right? These just random CVs here, but you calculate your bias potentials from your GAMD weights, and you achieve your unbiased PMF. So this is the general idea. We use the segments of the histogram identified based on the numbers of convergence points, which is a user-specified variable. And depending on the number of convergence points, like we saw before with the standard error equation, you want as many convergence points for every bin of data you get in your PMF, because that lowers the standard deviation, right? Or the standard error even. So here we can see the effect of increasing the convergence points. As you go up, you reduce the standard error, and I found that around 30,000 convergence points are required per bin for accurate reweighting. But obviously, when you do this, when you increase the number of convergence points, you're sacrificing the resolution for accuracy. And you can see that here, right? Because these minima, or these metastable states, as you could call them, they're all converging into one, or disappearing entirely over here in this top right as you increase the number of convergence points. You're increasing the accuracy, but you're losing data at the same time. So that's kind of the payoff with GAMD, right? You need a lot of data to get a half decent resolution with your final reweighted PMF. So what methods do we use in REST2? We used 13 replicas of each 1 microsecond long, all at different temperatures. In GAMD, we just did 1 microsecond simulation in OpenMM, and REST2 is in GROMACS. These are just 2 different toolkits to use any molecular dynamic simulation. The force field we use was Charm36M. That's just how you calculate the movements and the energies and such. Both we used 2 femtosecond time step. And then we recorded 100 times more data with the GAMD. Just because of that need, again, for to reduce that error, right? So to reduce that standard error, you need a hell of a lot of data. So we've recorded 100 times more data in GAMD. Whereas REST2, obviously, you don't need to reweight, so there's no need to have that much data. So Emma, you did principal component analysis, or PCA, of GAMD and REST2 torsion angles, which essentially just capture the main movements of the system, and we can reweight where needed after that. So here we can see the PCA, the REST2 simulation. Here you see these yellow lines moving along. So along the first principal component that has 21% variance, and the second principal component up here has 14%. And then moving along both CVs here. It's quite difficult to discern these movements as like actual, as them being different from one another or not just completely random. But it's because this molecule alpha G1 is quite small. It's quite difficult to actually tell those like definite movements, right? With bigger molecules, say like if you had a big protein and a lipid bilayer, it's a lot easier to actually see the principal components in action and actually discern their movements individually. So then we can use this robust REST2 data. Obviously, you know it's robust because it's just classic molecular dynamics. You can see here all the minima and the metastable states are very well defined. And we can just project the GAMD trajectory onto this, and that's what I'm going to show you now. So here we have the GAMD PMF, the unweighted one, the unreweighted one even. And you see here, like, it's very smooth. Like, you can move, like, it's easy to move between these states with ease. Like, a molecule would find it's very easy just to essentially skate over this PMF. And you can see here, after reweighting, you lose a lot of that data, right? You lose a lot of data over here, but you're also sampling more here than you are in the REST PMF, which is interesting to say the least. but the main thing is that you even with this less when you're receiving less data, because of this need for high convergence points, but you're actually keeping the global minima and the general shape of the PMF is the same, which is really actually quite important. And promising from a GAMD perspective, because it means that even when we've done 13 times less simulation time, you've still got a half decent PMF that's still finding the important points of data. And there's a very strong correlation between the REST PCs and the GAMD PCs, which is also important. But again, the post-processing is quite poor. The resolution is quite poor, so it is difficult to discern between individual minima, and you need more data to actually prove that this is exactly the same. So in conclusion, conotoxin conformations can be explored using GAMD, and GAMD is a hell of a lot more computationally efficient than REST2, and it does reproduce the essential data, but it suffers from those post-processing issues I've mentioned multiple times, and accurate reweighting requires a lot of data, and REST2 has 13 times the sampling time, so GAMD probably would have been a lot better off if it was a bit of a fairer matchup and we'd simulated for longer, but it just was not on the timescale. So yeah, thanks for listening. Oh, it's under 13 minutes. Boom. Yes. What a win. Oh, fuck yeah. What a fucking win. That's such a dub. That's such a dub. Yes. Under 13 minutes, baby. Under 13 minutes. Eat shit. Eat shit. Let's go. Cytos, that's why you'll never go anywhere with your life if you are just bored and not paying attention. Like that's just some pussy shit. I don't care. Go on, Lasty. What's the question? I want a question. Give me a question, mate. Bro finally looks decent and not looking like he hasn't showered in days. Nah, it's just the other camera. I swear it's the other camera. Finn, scroll up. And we totally do give a shit about this. But we all totally understand this. Now we do. We all will understand it. Just put the ice in the drink, brev. Put the pickles in the burger, bro. Nice. Motherfucker, you can't even take a derivative. Motherfucker, you can't apply anything you do to anything in real life. So shut the fuck up. What does any of this have to do with snail toxins? Well, I said at the beginning, right? That is a good question. That is a very good question. I'd be happy to get that question in the actual thing. So, all of these simulations were based on this alpha G1 conotoxin. And the end goal is essentially to build an inhibitor that outcompetes these cone snail toxins, right? So you can just inject the antitoxin and it'll outcompete in these binding sites and not cause your lungs to just fail, right? So to do this, we need to understand the conformations, and we want to do this quickly and easily and accurately. So we want to employ these enhanced sampling techniques to be able to understand their conformation, like the conformation means like what position all the atoms are in, right? So if we understand these conformations and how they're binding to this nicotinoacetylcholine receptor, then we can build a more competitive inhibitor that will outcompete these conotoxins in the body and create an antitoxin. So that's the end goal. But yeah, good question, Lastic. Good question. That was a great question, mate. Finn, Britain sold. They had almost a third of the world under their control at one point. Now look at how little control you have compared to back then. To be fair, mate, I actually wasn't alive. Nor do I give a shit. Also, we killed a lot of people and were very, very racist. So it's kind of a good thing that it's not happening anymore. So I don't know. Kind of a retarded point at them, but sure. I'll be honest, the first half was shit because you were stuttering and saying memes, but the second half you actually were locked in and cooked. Thanks, Fire. Does Finn actually work at BK? Yes, I do. Yeah. Got a job, mate. Get paid. I have another question. Who is Alpha G1? Alpha G1 is this bad boy here, Lastic, mate. It's the main conotoxin from the most, like, the cone snail that populates the most of the world. The most... How the fuck do you even say that? How do you put that into English? The most common. I'm retarded. Wow, I am retarded. Holy shit, I'm retarded, boys. Wow. Okay, I might be cooked. I might be cooked. What does Burger King have to do with chemistry? Money. I earn money so I can survive. I have to pay for uni. Everything costs. I don't live with my parents on them. His bills can't be that high. Who's going to be paying for my bills? Who's going to be paying for my bills? Could you elaborate on how the boost potential in GAMD is applied in your specific system? And how you ensure it captures the relevant degrees of freedom without over-smoothing critical energetic barriers? That's a shit question, Cytos. I mean, how I used... What? How the boost potential in GAMD is applied in my specific system. That doesn't make any sense. The boost potential is harmonic. It's Gaussian. It's the same in every system. Well, depending on the potential statistics, like I said. But I apply the boost potential to the dihedrals and the whole system. So everything gets a boost. Every minima is smoothened, right? So there's many different types of GAMD. You can have like LIGAMD, which applies the boost potential to ligand binding, which is what we would do when we understand the conformations, and we could just whack a conformation in the binding site and apply LIGAMD. So that would be a good idea. And the second part, how you ensure it captures the relevant degrees of freedom without over-smoothing critical energetic barriers. Right, so the over-smoothing critical energetic barriers is bollocks. That doesn't make any sense. That's rubbish, because that doesn't make any sense. You reweight. That's what you do. Over-smoothing is not a real thing. I mean, it kind of is, because the more boost potential you apply, the harder it is to reweight, and the more data you need to accurately reweight. And I'm going to blame ChatGPT, but it captures the relevant degrees of freedom. I proved it here. Not completely, because of the lack of data, but it captures the important points, the global minima, which is the most important points. It captures. And the correlation, the R values, you know about R values, you do maths, between the REST PCs and the GAMD PCs are really strong. I think between the first PCs of the GAMD simulation and the first PC of the REST simulation, it's like 0.99. So it's almost, they're like almost perfectly linear. And the second one is like 0.886, if memory serves. So this PC2 and this PC2 have a correlation of 0.886, which is good. It's very well correlated. So yeah, good question, kind of, ChatGPT. Finn, you're regarded, and you should retire and just play Mario games. SMM2 and Voxel will pay your rent. No, they won't. Here's a question: are Burger King onion rings overrated or underrated? It's extremely. I don't know if they're rated or not. But I would say this, Hunter. I make everything I eat fresh. I'm not the people that eat at Burger King. Eat the shit, like, I don't care what the fuck they eat. I don't give a shit. So I just put whatever we've got. If the burger's been sat there for 2 hours, they can eat that. I don't care. It doesn't bother me. But if I'm eating it, I'm eating fresh. Do you know what I mean? So my opinion is completely bollocks. Since when is chemistry this complicated? Like, I thought it was just a bunch of atoms and negative metal ions just bumping into each other and reacting and stuff. Right. Lastig, it wouldn't... What? I don't understand. Your chemistry is obviously more complicated than just what you learn when you're 15. So is everything. So is literally everything in life. Unless you just don't ignore it and work at Burger King your whole life. What specific aspects of GAMD PF, potential force, are you interested in exploring? Such as applications, benefits, or challenges? What is PF? I don't know what that means. If I look in ChatGPT what PF stands for. I'm 6'1", Hunter. Finn does gay chemistry. Gays make everything more complicated. Tell yourself that, mate. That's homophobic. What specific aspects of GAMD PF are interested in exploring? You just said that, mate. I need to know what PF is. Is it potential force? I don't know. I'm not 15. I never said you were elastic, but it swings and roundabouts. Fire, shut the fuck up, you gay retard. Alright, iDubbbz in 2016. No thanks. 6'1". Does bro get bitches? I have had a girlfriend for 3.5 years, to be fair. So, yes, I guess. You did say I was 15. Yeah. Did I? Oops. Well, I don't know. 16. There you go. Yeah. What can we look at? What should we look at? I think this slide is really good, where it shows the difference between enhanced. I like it when it plays, to be fair. When it shows the difference between CMD and enhanced sampling, that's pretty good, I think. People are going to be like, yeah, that makes sense to me now. Because the people I'm going to be talking to aren't retarded like you lot. But they also don't know what the fuck I'm talking about. But they'll understand a lot more than you lot. When applying GAMD to biomolecular systems such as proteins and nucleic acids, there may be a specific regions of the molecule that contribute disproportionately to the system's dynamics. I talked about that as well, such as active site, allosteric sites, or regions with high conformational entropy. Could you discuss how you determine which regions of the system are most critical to focus on during your simulations? Yes, Cyrus, I'd be delighted to tell you that, mate. As I said before, global minima, so these points here, the points of the least energy are what the conformation that is most likely to be occurring, right? So if you have this is true for any molecule. Molecules want to have the lowest energy possible. Statistically, they bump around and change shape all the time because of thermal energy, right? But at 0 Kelvin, they'll sit in the minima and they will not move. That's why 0 Kelvin is the lowest temperature you can have, right? They do not move after that. So they'll sit in the minima forever. So the global minima is the most likely state for them to be in. So we know where the global minima is in terms of these principal components. It's at this basically -2, -1 position here on this PMF. So we can look into the trajectory and find what that point actually looks like. Do you know what I mean? And then we can analyze that and think, and then we can put it in the binding site, and then see what it does in the binding site. And if it binds to the actual nicotinoacetylcholine receptor, we're in the fucking money. Do you know what I mean? So that's the next thing to do, essentially. But when we know the global minima, that's the most important thing. By far the most important thing. The rest of the PMF is important as well, in terms of conformations. Don't get me wrong, because it's possible for them to be in those conformations as well. They're possible conformations, so it's important for us to know about them. But the global minima is the key. The global minima is the key, always. And GAMD replicates that, which is good. Because it's a lot, like I said before, it's a lot more computationally efficient than REST 2, because you don't have to run all those replicas at the same time. What's CMD? CMD is conventional molecular dynamics, Elastic. It's essentially like the original CMD. It's like you're just integrating Newton's laws of motion over and over again, and it's really, really slow. Like I said before, because it doesn't, you get trapped in those energy minima because they're so big. It's the same within in real life. Like molecules won't typically move from those minima unless you simulate for unless you're moving right. So CMD. We'll go back to this figure here. So, this one's probably better. You get trapped in this minima, and it could take from a microsecond up to a second to get over this energy barrier. Statistically, just in true biology or CMD, because CMD or conventional molecular dynamics identically replicates real life. And it's just not possible on a computer. It takes way too fucking long. I did a microsecond and it took me 5 days. 5 days on a GPU. And GPU code is incredibly, incredibly fast in comparison to CPU code that's not parallelized. So it takes fucking forever to run CMD for a second. And it depends on how many molecules you have in your system, how many atoms and stuff like that. So my system's really small. It took me 5 days to run on GAMD. So it takes forever, right? That's the key issue in molecular dynamics. It just takes way too long. We are retarded because we don't like chem. No, you're retarded because you don't know. You're retarded in comparison to the people I'm going to be talking to. I might have went too far. I don't know what he said, Huntem. Finn VOD's official ain't ready for this. I like chemistry. It's just really hard. Nah, it's easy, mate. Fahrenheit's more than Celsius, more than Kelvin. Okay, you might be retarded, Huntem. Finn, your brain molecules must be minus 50 Kelvin because there is a negative motion going on in there. Holy L opinion. I agree with Cyrus on that one, mate. Finn is such a masturbator. Fuck yeah. Give me 3 facts about CMD. It's slow, it's computationally expensive, and you solve Newton's motions. Newton. I don't know how these fucking stutters like a retard in the actual thing. You solve Newton's equations of motions iteratively over the femtosecond timescale. There you go, hot fire. Lassie doesn't know about conventional molecular dynamics. Finn, you're autistic. Probably, mate, but there you are. You got to weaponize it. What is bro doing? Wavelengths now. Finn, you also good at physics? I'm good at quantum mechanics. It's my strongest thing in chemistry. But I don't do much physics apart from quantum. Finn can't do math to save his life. I'm way smarter than the average person you'll be presenting to. No, you're not, Sayos. No, you're not even close. You're not even close. You know a bit of maths. You don't know fucking... You know nothing about anything. There are 100 people. 99 are left-handed. Only one person is right-handed. How many left-handed people do you need to kill to make it so... You need to kill 49. 49? Was it 4? Yeah, 49. Bro is fucking acoustic. I'm right-handed. I'm smart enough to not do chemistry. Yeah, mate. This is what I mean. Good luck applying anything you do. Like, no one just does maths. No one just does maths. That's not a thing. You have to specialise in something. Otherwise, you're just going to be like, maths. I know maths, but I can't. Give me job. Job for maths. I want job for maths. I can do the integral on paper. Integral on paper. Oh, no, I'll just get a computer to do it in way less time. Oh, right. Okay, so your fucking job's pointless. So, yeah, good luck with that, Cytos, mate. Wrong. You need to kill 50. Oh. Yeah, that does make sense. Yeah. Yeah, you're right. You're right. To be fair, you can't get any job with just maths. No, you can, but you can't get a job doing just maths. Like, loads of my friends do maths degrees. Yeah, you can be a math. Yeah, you can be a teacher if you want. But fuck that for a laugh. Do you know what I mean? Right. Anyway. Fuck you, pussies. I'm out. I gotta do this presentation more. I need to really get it on about 12 minutes. That's the plan. Right. I'll see you all later. Yeah. Goodbye. Have a good rest of your day. Fuck you too. Oh, that's not very nice. Anyway, goodbye.